China. For thousands of years, it's proclaimed its greatness and power by erecting some of the greatest monuments on Earth. And as China roars back to world power status in the 21st century, it's once again proclaiming its power in steel and concrete, glass and stone. But even in today's China, it doesn't get any more amazing than this. In Beijing, China's capital, workers are constructing one of the most astonishing buildings ever built. When Beijing lights the Olympic torch, the eyes of the world will be on the incredible National Aquatic Center, a gigantic greenhouse that heats and cools itself, with a skeleton so strong it could stand on end and shrug off an earthquake, and a wafer-thin skin that puts out its own fires.
Can you imagine building a building out of this? Essentially, we're building a building out of bubble wrap, you know?
I have to say it's perfect. Okay.
What the Olympic crowds won't see is the sweat, brains and guts that got this megastructure built. The struggle to believe in the incredible.
I think we're all a bit stunned, really. But you want to do what?
The lives put on hold.
My wife didn't want to speak to me for a while.
And the hard hat high wire acts 30 meters high.
It looks a bit crazy, but it is safe.
The National Aquatic Centre's a visionary piece of eco-architecture and a brilliant monument to 21st century China. And it's also a tribute to a team that conquered fear and doubt and didn't quit until they'd made the impossible a reality. Beijing. Building materials arrive at a construction site. Hardly unusual in this construction-crazy town. But these building materials and this building are different. Really different. 90 kilometers of steel, 22,000 beams, following no conventional straight lines, a maze of metal. That's enough steel to circle more than 200 Olympic running tracks. And it's covered with plastic, 100,000 square meters of it, enough to cover 14 full-size rugby pitches, cut into cushions as big as 9 meters in diameter, but only 0.2 of a millimeter thick, nearly 8 times thinner than a penny. Officially, it's called the National Aquatic Center, but in the world of mega architecture, it's known as the water cube. It's a fantastic honeycomb that looks as light and fragile as a tinker toy. But in reality, it weighs 6,500 tons. That's almost as heavy as all the metal in the Eiffel Tower. And inside its walls and ceiling, nothing but air. There is nothing else like it. Who came up with this amazing building? Engineering team leader, Tristram Carfrey. Architects John Billman, Mark Butler and Chris Bosse. Fire engineer Marianne Foley. Structural engineer Mark Arkenstall. Building modeler Stuart Bull. Environmental engineer Heiko Scheppers. Chinese design team project manager Yi Hongtao. Part of a 100-strong architectural and engineering dream team. A team that envisions the original, the astonishing, and the apparently impossible, and made it into a megastructure. Sydney, Australia, 2002. The architectural firm of PTW and the structural engineers of Arup Australia team up with a Chinese consortium led by China State Construction Engineering Corporation and go after one of the world's most coveted construction contracts. From day one, the pressure's on, because they're literally racing the clock. A giant clock in Beijing's Tiananmen Square, counting down the hours and seconds to the 2008 Summer Olympics. China has invited the world's greatest architects and engineers to transform Beijing into an Olympic host city like none ever seen. The Chinese-Australian team's goal: to design and build the Olympics' prestigious swimming venue. And right away, they run smack into a heart-sinking challenge. The Olympic National Stadium, aka the Bird's Nest. A mind-blowing masterpiece only 1 kilometre from the site where the swimming centre would stand.
When we saw the stadium design, I thought, oh, jeez, how can we match this? We were going to set our aims to create a building that was equal to the stadium, and then we saw the stadium design, and I think all our hearts fell on the ground for that moment. We just thought, oh.
The team searches for a design that will knock the judges' socks off, and searches, and searches, and searches. And then, after nearly 6 weeks of failure, and with the completion deadline looming, the eureka moment. Soap bubbles. Despite their random appearance, soap bubbles always cling together in regular patterns, in 12 and 14-sided cells, nature's most efficient division of space. And despite their flimsy look, an infinite array of connected soap bubbles has a geometry that's just right for a high-tech building. Strong enough to be the model for a megastructure.
3 soap films always come together at 120 degrees, like a Mercedes symbol. And along that line, right, the 3 symbols come together, there is an axis that we can use as a piece of structure. So we can put a pipe down that line. Those lines always join 4 to a node. We can stick a joint in, we can pull in 3 more pieces, we get a structure.
At last, the team has a design bold and original enough to win the competition. What they don't have is time.
I probably slept 2 or 3 hours a day. I took a nap when I felt tired, and an hour later I'd get up to work. Almost everyone in our team was the same. Everybody's eyes looked like rabbits, very red. We had tremendous pressure. After we agreed on the water cube's design, we had 5 weeks to prepare a building of this complexity. It was extremely hard.
Hardest of all, making a model to show the judges what the finished building would look like. No one knows if modeling such a complex building in only 5 weeks is even possible.
Well, we were desperate at the time. We had 2 weeks to go, and we did not know how we were going to make our model.
In Melbourne, they find a company that's at least willing to try. ARC Australia specializes in a process called rapid prototyping, using a computer-guided laser to carve a model of a new product out of a vat of liquid epoxy. By etching it in layers only 1/100th of a centimeter thick. Over the years, most of its clients have asked for models of products like water jugs, toothpaste tubes, and auto racing helmets. And then, in 2003, prototype manager Peter Lucas gets an urgent call from the Watercube team.
They'd spoken to other model makers who said that they couldn't make this design. So they approached us and was really their last port of call as far as getting a model made. We wanted to do it because it was a difficult model, and it was something a little bit different from the normal day-to-day jobs that we do.
But within a few days, ARC is pondering that old saying, be careful what you wish for, you might get it.
The machine kept crashing. The file was so big, it was like a 20 meg file, and most files we're dealing with sort of 2 to 5 megs. The darkest hour was when we thought, no, we can't do this. So what we decided to do was to grow the water cube in sections, and what PTW, the architects, did was that they came down with hand luggage, and we loaded each section into the hand luggage, and they flew it back to Beijing. I think the time pressure was down to hours at that stage.
The finished model just meets the competition deadline. The team waits for China's decision. They know that losing will be hard, but they also know that winning and having to build something never built before might be even harder. July 2003. After nearly 4 months of 7-day weeks and working day and night, the Watercube team gets the news. Voting online, the Chinese people have picked the Watercube design to be the Olympic swimming center. The team's reaction, rejoicing, followed by panic.
And really, it was only when they came back from the competition and actually had some images and this is what it's going to be. And I think we all had in our minds that it was some sort of simpler swimming centre. I think we're all a bit stunned, really. Like, you want to do what?
There's been an immense effort to win. And when you're in a winning mode, you don't necessarily focus on all the difficulties that are ahead. You want the job. You've won the job, we sit down, we look at it, and there is a bit of a heart sinking, I think, in a sort of, oh my God, can this actually be done?
And in fact, Chinese authorities were asking the same question. China had voted for a building like no other. Now, its designers had to prove they could actually build it. The Watercube's gigantic steel honeycomb had 22,000 steel beams, following no conventional straight lines. A crazy-looking pattern. Its roof and walls would have to be 100,000 square meters of bubbles, made of something light enough and flexible enough to cover this apparently random maze of steel, but strong enough to stand up to Beijing's desert sandstorms, broiling summers, and sub-freezing winters. Glass, too heavy and brittle. Concrete, a design disaster. The answer came from way outside the box. Meets the amazing ETFE.
That's a piece of ETFE. Fantastic, isn't it? Can you imagine building a building out of this?
ETFE stands for ethylene tetrafluoroethylene. Chemists call it fluoropolymer. The rest of us call it plastic.
Essentially, we're building a building out of bubble wrap.
It may look like freezer wrap or a dry cleaning bag, but ETFE is a plastic like no other. A plastic with a past. In 1938, an American chemist at DuPont Chemical Company was experimenting with gases and accidentally created a new substance, known around the world as Teflon. Since 1960, Teflon's helped millions in the kitchen. But most people have no idea it hasn't always been a labor-saving coating on their frying pans. Originally, Teflon had a much more serious purpose. During World War II, scientists used it to coat the gaskets inside the first atomic bombs, to prevent corrosion and ensure success.
Just 50 seconds later, 15 miles from ground zero, the Enola Gay rocked at last.
By 1970, America was sending spacecraft and astronauts beyond Earth's atmosphere and needed to protect them against cosmic radiation. So NASA and DuPont tweaked Teflon's chemical structure and created ETFE. The 1960s and 70s also saw the rise of the geodesic dome and other architectural innovations. And it wasn't long before architects and engineers grasped ETFE's potential. The miracle plastic that had once helped transform cities into rubble would now help transform them into futurescapes. The sun's ultraviolet rays can't hurt ETFE. Samples created decades ago still look brand new. It's just 1% of the weight of glass and much more flexible. Incredibly, it's also more transparent than glass and lets in more light. And thanks to its space-age origins, it's a superb insulator. Today, ETFE covers some of the world's most impressive structures, like the Eden Project in Cornwall, England, and Munich's Allianz Arena, host site of the 2006 World Cup. But the water cube's 100,000 square meters sets the record as the biggest ETFE construction in the world. An impressive statistic that worries Chinese officials. They ask, what will happen if 100,000 square meters of plastic catches fire, with 20,000 Olympic spectators inside? To win approval for ETFE, Arup's lead fire engineer, Marianne Foley, has to change some minds fast. And the first mind she has to change is her own.
When I was first presented with, this is what we're going to do, it's like, you're going to be kidding, you're going to cover the building in plastic. Because, you know, obviously my thoughts were the typical ones, like, there's going to be huge flames licking up the side of the building, and that's not going to be good. We all got visions of what plastic may do in the event of fire, and we're sort of envisaging big fires and raining flaming droplets down. And there's plenty of material, plenty of plastics behave like that.
But Foley soon discovers that ETFE doesn't behave like other plastics. She researches the worst-case scenario, a fire in the water cube with some 20,000 Olympic spectators inside, and asks, what will those 20,000 people see?
But you're not going to see what you know, the movies show you, for example, of flames licking up the outside of a building and you know, the towering inferno kind of stuff. You're not going to see any of that. I mean, the likelihood actually is you would see nothing at all, which is a terribly boring answer.
Inside the cavernous water cube, flames will have a hard time reaching the ETFE skin. But what if they do? At the water cube's ETFE factory in Beijing, a demonstration reveals what will happen. If a fire does reach the ETFE skin, the skin won't burst into flame. Instead, ETFE will just melt away. But only as long as the flame stays on it. Take the flame away, the melting instantly stops. It looks like magic, but ETFE expert James Murphy knows it's just good chemistry.
ETFE has a chemical in it, fluorine, sort of like the chemical that's in your toothpaste, and that puts out the flame. The fluoride in the ETFE prevents enough oxygen from being present to sustain fire.
No matter how long fire touches it, ETFE doesn't burst into flames. It melts and drops away.
And that's a big benefit because it allows all the harmful gases and smoke out of the building, and that allows people to see and get out safely.
What you're essentially going to see is what looks like a very large piece of cling wrap shriveling away from a lighter flame. It's just going to shrink away, and you're just going to get a hole. And then people evacuating.
The design team proves that if the water cube's skin caught fire, it will simply wrinkle up and blow away. But what will happen to its immense steel skeleton? A fire can make steel so hot, it weakens and gives way. China's fire code requires spraying steel with a fire-resistant chemical coating. Very effective, and very ugly. The team argues that given the building's vast amount of visible steel, fireproof slurry will make an Olympic masterpiece look like a gigantic bowl of porridge.
It's a terrible material, actually. The idea that we would have had to do that to that building it just makes me laugh, actually, because, there's just no way.
But to win that argument, the Watercube team has to prove that their steel honeycomb will survive a fire on its own. And that means burning some midnight oil.
In here that we have the problem with the two beams.
We had to look at how fires in the building would affect this very intricate structure. That level of complexity was not something I'd done before, and it's not something you would normally do.
Foley painstakingly analyses the Watercube's design to determine where fires are likely to break out and what part of the building will be most vulnerable to fire. While her fellow engineer, Mark Arkenstall, calculates how strong the steel frame will have to be to withstand a fire without a protective coating.
My role as fire engineer was to work out what sort of fires we could have, like how big were they going to be, how close to the steel would they get, and from that to work out what a temperature distribution would be. So what temperature was it going to be where on that steel? And then Mark took over from there and he worked out what that would do to those elements that were exposed to the high temperature, and where that temperature was such that the element would no longer carry the load. If that stopped doing that, what did the rest of the structure do?
To their vast relief, this analysis reveals that the Watercube's steel honeycomb will survive a major fire. If any beams melt in extreme heat, the surrounding beams will shoulder the load and keep the building from collapsing. 20,000 Olympic spectators inside the Watercube are now looking safer. But the Watercube still has to satisfy one more fire regulation, and it's another potential design wrecker. The Chinese fire code requires a building holding 20,000 people to have 200 meters of exits, nearly the same length as two sides of the Watercube. The code also requires public buildings to have fire-protected enclosed spaces like stairwells leading to fire exits. But the Watercube encloses nothing. Inside, it's a vast open space. So the design team goes back to the drawing board and goes the extra mile to convince authorities that their design is safe. Even though tests show that ETFE will melt, not burn, and will allow smoke to escape a burning Watercube, Marianne Foley models the probable pathways smoke and flame will take and positions sprinklers and smoke extractors along those routes to make doubly sure that fires will go out and smoke will be sucked out of the building. She argues that with these extra safeguards in place, enclosed escape routes and 200 meters of exit doors aren't necessary or even effective.
People don't actually use those. They don't like them, they don't know where they go, they're afraid of them. We all like to leave a building the same way we came in, or at least a way we've mind mapped. So we know how to get out, we know where we're going to go, we know what it's going to look like.
Impressed with the team's arguments, Chinese fire experts approved the Watercube's design without any changes.
It was wonderful. Our peer reviewers said that we had essentially done state-of-the-art engineering, that they thought what we'd done was fantastic and that they fully supported it, which is nice to hear.
But fire isn't the only thing the authorities were worried about. Can the Watercube's gigantic honeycomb survive in one of China's deadliest earthquake zones? There will be plenty more long days and sleepless nights to come. In 1976, a single earthquake killed 240,000 people, only 180 kilometers from Beijing, where the Olympic Swim Center will stand. With the Olympic countdown clock ticking, the heat is on to prove the water cube can survive an earthquake. And Arab engineer Mark Arkenstall is definitely feeling that heat.
From a structural engineering point of view, we had to be confident that this very complex building would stand up in Beijing with earthquakes, wind, snow, you name it. And it's not just like designing a warehouse. It's actually the water cube. It's just so much more than anything you'll ever see anywhere.
The challenge, how to make the water cube steel honeycomb strong enough to stand up to high winds, dust storms, snow, and earthquakes, but light enough so it won't collapse under its own weight. After cyber testing 190 different scenarios, the team proves that despite its resemblance to the world's biggest Tinker Toy, the water cube will fare extremely well in an earthquake.
Most big structures in earthquakes resist the forces simply through strength. What happens is that the ground shakes, there's a momentum or an inertia in the building, and so it has to move with the ground that's shaking, and that creates enormous forces or stresses in the building. In our case, what we get is that as the ground shakes, the structure goes plastic, that is, the steel begins to yield, it moves the force onto somewhere else. Okay, so it redistributes within itself.
In fact, the water cube's 22,000 steel beams and joints give it a greater capacity to absorb an earthquake's energy, probably more than any other building ever built. Seismologist Han Jian says the cube's design beats quakes by bending so it won't break.
一般这样的结构的，我在地震现场看过。
I studied damaged building structures at earthquake sites. I found that wooden and bamboo structures are very resistant to quakes.
一般都还抗震能力都很强的。它这个水体那个又比较轻，所以在
Like the wooden structures I studied at the earthquake sites, the water cube is very resistant because it is flexible.
也是比较强的。
But one more challenge remains. The water cube's builders need a 3D computerized blueprint, a virtual model that assembles the entire building in cyberspace. And it's up to building modeler Stuart Bull to make that happen.
I was scared silly. I knew that as the job went further, it would get harder for me personally.
Bull has 7 months to accurately model the water cube. That may sound like a lot of time, but not for a building made of 22,000 irregular steel beams.
You then have the stress and thinking, right, I've got to get that done. I've got to get that done now. Why doesn't this work? Go back to the beginning. You get it to work the first time, but it doesn't work the second time. Why doesn't this work? We broke so many computers. They physically stopped working. It was not funny. My wife didn't want to speak to me for a while. Just puts me away in the spare room and say, well, you can come out when you're finished.
Several months and several dead computers later, Stuart Bull is out of the spare room, and the water cube's builders have accurate blueprints. Now, they have to build it. Construction starts in December 2003. Workers pour the immense foundation, then begin assembling 22,000 beams of steel. It's a mega challenge, and they tackle it head on.
The steel structure is very difficult. There are tens of thousands of parts and link points, and you have to put all this together and accurately precision them. Also, Because we use high-strength steel instead of usual steel, it became unusually demanding for the welding job. We need to make sure of the quality of welded joints to prevent collapsing.
能够保证它焊缝的质量，而不至于产生，比如说如果你焊不好的话，有可能就会
It is a huge challenge.
这样一种后果，那么不至于产生这样的后果，这是一个很大很大的挑战。
Well, if the water cube was to be built in Australia or the UK or America, the builder most probably would have taken a modular approach in that they would have built large segments of the structure and lifted them into place, and they would have welded the seams of these modules together. However, in China, an army of welders and workers simply put the beams together, and the structure literally rose out of the ground and marched up the walls and across the roof and then down the other side, and then it was built.
By August 2005, the water cube's gigantic steel lattice looms above the Olympic green. It's time to cover it with ETFE. And while building its massive skeleton calls for heavy lifting, manufacturing its super thin, super light skin requires some serious mental gymnastics. At this Beijing factory, workers are transforming huge sheets of ETFE into 3,500 water cube pillows. Every one designed in Germany. In Beijing, technicians translate each pillow's unique dimensions from a German computer program to a Chinese database, calculating how to cut each piece of ETFE with the least amount of wasted material. While other workers stretch huge sheets of ETFE over a giant vacuum table, sealing them flush with the surface. Then, the computer program guides a blade as it cuts each pillow to its exact dimensions. Every finished pillow must be exactly as it was designed. For factory owner Stefan Lienert, that meant some sleepless nights when manufacturing began.
The thing is to have these cushions, every one of them, manufactured to the precise dimension, have it done on the right day, in the right position, for the team to be installed in time. If there was one thing wrong, it would have been wrong for every single cushion, which would have been a technical disaster, but also a financial disaster. Luckily enough, our programs seemed to be all right, so everything did fit. And actually, out of the 3,500 cushions, we had to do one new cushion because we actually did make one production error.
From the moment they're cut to shape, keeping track of the pillow pieces becomes an obsession. They're numbered to match the water cube blueprint and stored in identically numbered bins. Workers weld a rope into each pillow's edges so that they can be clamped into an aluminium frame. Last step, quality control. The factory tests, installs and inflates every pillow. If anything's wrong, now's the time to find out, before it's delivered to the water cube. Every mistake costs time, and time is running out. Installing the water cube's 100,000 square meters of ETFE pillows isn't any easier than making them. James Murphy manages ETFE production and installation for the water cube. To get his ETFE pillows to their positions, workers must erect a massive scaffold out of hundreds of thousands of pipes.
We built a rolling scaffold, and we do literally 1/3 of the building. We put these rails in place, we finish our work in this area, and then we push all of the scaffold forward on the rail. And then we mobilize in that area, we finish that work, and we repeat the process again. The scaffold is safe. It looks a bit crazy, but we've been at it now 2.5 years, so it is safe.
Once the scaffold's in place, installation begins with some low-tech sweat and muscle as workers hand carry the ETFE pillows over 30 meters up. And they do sweat. At the top of the scaffold, the temperature under the roof is about 10 degrees hotter than the floor where they started. In summer, it can reach over 50 degrees. In this often searing heat, workers must carefully complete the complex process of blowing some of the world's biggest bubbles. First step, unfold the ETFE pillow and rotate it until it matches up with the frame and the steel structure it was designed to fit. Next step, clip the pillow into the framework, a critical step that's got to be done right, because the steel frame stretches the installed pillows tight in a gigantic web, balancing force and counterforce.
You can get the equivalent of every 3 feet or a meter, about the weight of one Volkswagen Beetle pulling horizontally. That force is balanced, counterbalanced by a force from this other cushion over here coming through that bracket. So everything balances out, and that makes it an extremely efficient system.
Building the water cube means doing this 3,500 times. An impressive amount of work. But it's the pillow inflation system that reveals some of the water cube's most ingenious eco-engineering.
Air is part of the structure. The cushion is not a structural cushion without air. So air keeps our building up, which is fundamentally different from all other building systems used in the world today.
And believe it or not, it's a very small amount of air, so that makes the power consumption extremely low, equivalent to your refrigerator in the kitchen. So you get very large surface areas of cushions filled with air very cheaply. So you can see here at the base we have a big pipe that branches into a smaller pipe, and the further we go up it gets smaller. That's mainly to save on materials and to make the building more environmentally friendly, not to dump energy into the materials when it's not required.
But a building that's 30 meters high and 70,000 meters square must surely need an energy-gulping mega pump to keep 3,500 pillows inflated. Wrong. The water cube's divided into 18 inflation zones. Each zone has its own fans that send air to its cushions. A sensor in each zone signals the fans if the pillows need more air, or if it's fully inflated, turning the fans on or off as needed, using no more than the minimum required energy. An inflation system that can keep 100,000 square meters of ETFE inflated at just the right pressure, without wasting energy, is good engineering indeed. But the building's most environmentally friendly feature doesn't need any hardware to happen.
One of the key things when we design a sustainable building is we actually look at the climate. In Beijing it gets to minus 13 degrees.
And that's a problem, because after the Olympics, the water cube will be Beijing's year-round swimming center.
You can imagine minus 13 degrees and everybody's running around almost naked. So it needs to be very warm in that space. It just makes a lot of sense to design a greenhouse to heat everything up under those conditions.
Thanks to ETFE, heating the water cube in winter won't be a problem. Building its roof out of ETFE cushions will be as energy efficient as building it out of solar panels. The ETFE's skin will trap 20% of the solar energy falling on the building and use it to heat the interior and the swimming pools, and let in so much daylight that some areas will save over 50% of their normal lighting bill.
Why did we use the transparent cushions? So that the interior could be lit by daylight until very late in the day. It saves a lot of lighting cost. At the same time, the sunlight can heat up the water as well as the interior temperature. We estimated that we can save up to 30% of energy than a conventional stadium.
ETFE's greenhouse effect makes the water cube a brilliantly sustainable building, but only for half the year.
Our problem is actually more to do in summer when it is 31 degrees in Beijing, and how do we make sure it doesn't get too hot in the space.
The same greenhouse effect that makes the water cube cozy in winter makes it an oven in summer. Somehow, it has to cool itself as sustainably as it heats itself, without using too much energy. And that's where these dots come in. They look unremarkable, but don't judge them by their looks. Thanks to these dot patterns built into its skin, the water cube can efficiently regulate its temperature, keeping cool in blazing summers with minimal help from air conditioning. The dots reflect solar energy away while letting daylight in. The thicker the dot pattern, the more heat stays out. The thinner the pattern, the more heat gets in. And how thick or thin the pattern depends on where it is.
We change the amount of print on each cushion based upon what activity is happening in the room. We're standing in a place that will be a bar eventually, so during the day people will be sitting down relaxing. They don't want to be overheated by the sun energy coming in and making the place uncomfortable. So we put a very high density, many dots together, close together, up to 55 or 60% of the surface area in these areas allow us to reduce the cooling load by up to 40%, which is extremely efficient. So when you look around the building in here, we have less than 20% frit on this cushion. On the outside we have 50%, and then around the structure we have about 10%, which again optimizes every part of the building to reflect out that heat energy from the sun, but to let in the light energy to cut down on the artificial lighting needs for the building. And that is basically the magic and wonder of print on ETFE cushions.
And there's one more way that ETFE makes the water cube a wonder of sustainable architecture. Something that explains why these workers have to toil in temperatures up to 50 degrees. When it's finished, the ceiling they're installing will be where the water cube stores its own self-generated energy between outer and inner layers of ETFE.
We have two skins of these ETFE bubbles, and we capture the energy in between the two skins. In winter, that energy stays where it is. We essentially seal the whole box and capture all that energy. In summer, we ventilate that out. We open up the ETFE bubbles at low level and high level, and we flush that energy back out of the building.
We have seat fans for audiences. It only lowers the temperature within the spectator area. The athletes won't be affected. They are quite sensitive to the temperature change. Also, our natural ventilation solution helps exchange air between inside and outside. We save heat to heat up the pool. We also save rainfall for the water.
ETFE seems invincible, but even this super plastic has an Achilles heel. ETFE can withstand decades of ultraviolet radiation and heavy loads of wind and snow. But it's so thin you can cut it with a knife. Maintaining a building made of 100,000 square meters of wafer-thin plastic in a hot, cold, wet, dusty, polluted urban world requires some special attention and some special training. Water cube maintenance isn't like caring for other buildings, and it's not for the timid. ETFE supplier Vector Foil Tech trained a special Chinese team of abseilers to inspect and repair the outside pillows. Today, one of those workers finds and fixes a small hole torn in a pillow when a water cannon sprayed the building to wash away Beijing's formidable dust. But even in ETFE's fragility, its champions see its strength.
Typically, when you aim a water cannon from a fire engine at any building, it tends to break, and usually it would knock a wall down. A masonry wall would be totally knocked down, but our cushion had a small hole and kept on going about its business as though nothing had happened. So what we've done now is just come down on the side of the building to create a temporary patch to stop rainwater going into the building. And we will then come back with a much neater patch and reapply it, and then over time you won't even see the patch. The cushion has this self-healing property because it's under pressure. That's the great advantage of ETFE, where we can just make a small repair, the building keeps on going in operation, whereas if it was glass or another material, you would have to completely replace that panel and it would be a major operation.
Summer 2007. Inside the water cube, workers install and inflate the final ETFE pillows. Outside, its finished walls and roof are already revealing what a mind-blowing masterpiece the National Aquatic Centre will be.
I don't think anybody would have walked away from this project from day one, no matter what they may have thought in their own private world, this is too hard or this is too scary. Everybody wanted to get to the end and achieve what we thought at the beginning was the impossible.
To be honest, I actually don't know to this day how we did it. It was just such an extraordinary thing.
You don't get great building designs if you do what's easy.
When the water cube's finished, China will proudly unveil its latest wonder of the world.
It is founded by Chinese all over the world. It represents their hopes and dreams for Chinese Olympics. Its design is under Chinese leadership, which is not common for iconic buildings. Its construction is totally by Chinese, achieved by our own innovation. So it is something to be proud of.
Experts like Tsinghua University's Zhou Rong are already declaring the water cube as great as the monuments of the past, but brilliantly proclaiming the China of today.
In the
21st century, we shouldn't see the water cube as a modern-day equivalent of the Forbidden City and the Great Wall. Unlike the Great Wall, the water cube is really transparent. You can see through it. And that really is a new image for China. Now the water cube will represent that image to the outside world.
I have to say it's perfect. Okay.
On day one of the Beijing Olympics, athletes, spectators, and TV viewers everywhere will marvel at this megastructure like no other. And all the people who worked so long and so hard to dream it and build it can finally relax.